So, good afternoon, everyone. Today we are going to do the week 8 assignment related problems, and we'll be starting in 3 minutes.
Good evening, ma'am.
Good evening. We'll be starting in 2 minutes, okay?
Okay, ma'am.
Okay, let's start. I hope my screen is visible. So, the first question is, what is screening? So, screening is a process of separating a mixture of particles of different sizes, right, into two or more number of fractions. So suppose there are bigger particles, okay, different sizes particles are there, very small to very big. A mixture is going through a screening machine. It will form, it will separate the particles. First, it will separate the bigger one, then the middle one, and then the final one. And how this is separated? This process is called the screening. So let's see the videos first. So if you see the feeding is happening from the left side, feeding of mixtures. This is the overflow, and where overflow in this overflow there is water. Suppose we are separating dust particles from water mixture. So we are separating here, the overflow is the water and heavy minerals are the underflow. So this is the screening technique. Excuse me. So this is the lab scale sieve shaker, which we have almost everyone have has seen this. So they are giving some bigger particles and shaking. So what will happen? So when they have used the ball, so these are bigger from the mesh opening, right? So that is why it is not going, it is just vibrating in the same plate. Now they are using sand. Now when they are using sand, you will see what is happening here. Here the sand particle size is very smaller than the mesh openings, right? So this time is will operate for a duration of 10 minutes. Okay. Then so inside the sand there are different sizes of particles, right? Different shapes of particles are present. So that will be separated in accordingly in each of the sieves. So this is the sieve concept. Now let's learn what is the sieve openings and all. Okay. So what we have seen that this is the bigger sieve, then under it suppose another sieve is there, suppose another sieve is there, and finally there is a pan, right? This is a pan. So this is the final sieve is called the pan, where only the underflow particles are remain. So screening is accomplished by passing the materials in an open cylindrical container with uniformly spaced openings of the desired size at the base of the screen. So you have seen that here this is the base of the screen and there is this mesh. These are called mesh. So it is of different size. So as we go down, the mesh size will be decreasing, right? Similarly here also. Similarly here also. Okay, so the screen through which the particles have passed is called the limiting screen. Suppose I am sending mixture of particles, okay? So in the top mesh, only the bigger one will retain, right? And all the medium and fine will pass through, right? In the second case, in this mesh, medium one will retain and the fine one will pass through, right? So that is good. The screen through which the particles have passed. Suppose we are considering this screen and the particles have passed. That means here the fine particles are passed. So this is the limiting screen for fine particles. Limiting screen for fine particles. And materials that remains on a given screen surface and which has retained the same particles is called the retaining screen. So, and for medium sized particle, this is called the retaining screen. So it will be dependent on particle to particle basis. For bigger particles, this is the retaining screen, and for medium particles, this is the limiting screen. So this will be dependent on the particles. Now, what is this mesh and opening? We will know. So suppose this is the suppose that is a mesh, right? Or sieve. So the minimum clear space between the edges of the opening in a screening surface is called the aperture. Okay, so what is aperture? So this distance between these two openings is called the aperture. This is the aperture. And so if we focus on one mesh, so it will look like this. So this is a cylindrical kind of thing and there is this opening, right? Another thing is there and another thing is there. So from this, the whole distance is called the aperture, and this medium portion is called the mesh. So if somebody says that 20 mesh opening screen means the screen will have 20 opening per inch. So this is the basic definition of mesh and aperture. Okay, so this is the screening. Next question. The oversize or tail pass through the screen openings. Undersize or fines do not. Is it true or false?
True.
No, it is false because I have said oversized particles pass through. Oversized
So
particles doesn't
under.
pass. Undersized particle pass through. So it is the opposite one. So
Hmm.
oversized, undersized or fines pass through and
Okay.
through the screen openings, and oversized tails do not. So this is false. Next, a single screen separates the solid mixture into what number of fractions?
So, 4.
No, it is 2. Minimum 2. It can be 4, but minimum 2. So that is, it is 2. Next. The ratio of actual mesh dimension of any screen to that of the next smaller screen is what?
1.41, that is
Yes,
equal to root 2.
yes, this is 1.41. Next, which is the common metal used? Which is the common metal used to make industrial screen? Which is
Stainless
the,
steel.
yes, the answer is stainless steel. Next question. How are screens agitated? How are screens agitated?
Shaking, grinding, vibrating.
Hmm.
Mechanically, yeah, electrically.
Anything. How? Yes, so mechanically also it can be agitated, electrically also it can be agitated. Mechanically, electrically, and under the mechanical, there is shaking, then there is vibrating or gyrating, vibrating or gyrating. Okay, so these are the screen's agitation process. Next, describe the type of different type of screening equipment. Describe the different types of screening equipment.
Stationary, visual, live.
Yes,
vibrating
so
screen.
if we see the videos, it will be clear. So if you see this stationary grizzle, you can see that it is constantly vibrating also, and mixture of feed particles are there, some of the bigger size and some of the smaller size, and they are separated through this mesh. It's feeding oversized particle, abrasive resistant plates, and double grizzly material. This is rugged structure. This is the lifting hook, and this is the slide plates for supporting. So you can see inside the how these meshes are formed. It is a different type of mesh what we see from in our lab scale. So they are this mesh screen are very hard so that it won't get damaged due to this solid particles, hard solid particles. So these are the parts of the machine. Next one is the gyratory or vibrating screen. So for the fine mesh in the medium, this is the coarse mesh. So you can see that this is the whole system is shaking or rotating, and particles are separated with the size of the mesh. So this is the feed from here. Feed is coming. This is the oversized particles. This is the fraction 1, fraction 2, and different size of oversized particles. And this is the fine particles are separated, which is called here the underside. This is also another type of vibratory screen. You can see these different meshes inside it. So similarly, from top there is input, and this is the discharge, that may overflow and oversized and undersized particle discharge. So now all the particles are separated. Last one is the centrifugal shifter. This is a horizontal cylinder of oven metal and or plastic. So these are the safety interlocks. So here the meshes are set up in a vertical direction, and that is how with this helical paddles they are separated. So you can see that screen powders and granular materials are coming feed as a feed, and with the help of this helical paddles, the dry or moist materials are separated from here, separate liquids and solids from this portion. This is the dust-free operation. Fine particles are collected from the bottom. So these are the 4 types of screening equipment used in the industry. Next, the bar spacing in stationary greases is what?
50 to 200 mm.
Yes, the answer is 50 to 200 mm. Next, at what angles two screens are aligned in a gyratory screen? At what angles two screens are aligned in a gyratory screen?
30 degree,
Yes, two
16
screens
and
are, one is 16-degree and one is 30-degree with the horizontal. So one is 60-degree and one is 30-degree. Next, what is the rate of gyration? What is the rate of gyration?
answer B, 600 to 1800 rpm.
Yes, this is to 600 to 800 rpm. That is very high speed. Next, what is the typical size of a gyratory screen? What is the typical size of a gyratory screen?
Rectangular.
Yes, it is. The screens are rectangular and long. So these distance are mentioned here. That is the from 0.5, 1.2 to 1.5 to 4.3. Mainly this the long and rectangular. Next, horizontal cylinder is used in centrifugal shifter. Is it true or false? Horizontal cylinder is used in centrifugal shifter.
True. True.
True. Yes, the answer is true. What is screen efficiency? What is screen efficiency?
The screen is separating the material A and B,
Yes,
or
measure of
underflow.
measure of separating two particles. Measure of separating two materials as underflow and overflow. As overflow and underflow. Next, derive the overall effectiveness of a screen. So this is given in the lecture note, but still I am doing for practice because you have to
Okay.
remember the formula for uh, solving the problem. So suppose this is your screening machine. From here, feed is coming. This is the screen, and this is your overflow. That is, the overflow means your desired particle. Your underflow also can be your desired particle. So you have to be very careful while reading the questions. Which one is your desired particle? Depending on that, you have to solve the problem. And bottom one is the underflow, which we do not want. This is B. And now what will happen that now the mass fraction of your desired particle in feed is,
F equal to D plus B.
suppose, yes, suppose XAF. Here your desired particle, the overflow contains XDF portion of XAD, sorry, XAD portion of the desired particle, and underflow contains XAB portion of your desired particle. So in each case, then in your feed, what will be the amount of this 1 minus XAF will be the amount of undesired particle in feed. Here it will be 1 minus XAD, and here it will be 1 minus XAB. So this is the concentration or fraction of desired particles and undesired particles in the screen, in the feed, overflow and underflow. And now we'll do the material balance. Simple material balance, if we do, what will happen? It will be if the flow rate F equals to D plus B. This is the one equation, and second equation is F XAF equals to D XAD plus B XAB. So these two are our material balance equation. Now if we want to remove, suppose D, or from, or you can remove the B also. So if you want to remove B, we have to multiply everything with XAB. So what will be both the equations with XAB? So And if we moment. So if you do this now, so if we multiply with xab, because we are eliminating b, we want to eliminate b, so multiplying with xab, what we will get? So if you notice, so what we will get? First equation we are multiplying, so it will be fxab equals to dxab plus bxab, and the second equation will be as it is, that is fxaf equals to dxad plus bxab. Now if we subtract these two, so everything will be minus minus, and here it also be minus, that means these two will be cut out. So what is left? F into xab minus xaf equals to d into xab minus xad. So from here we can get the ratio of overflow versus the feed, that is d by f equals to, if we change the position also, then it will be also same, that is xad minus xab divided by xaf. No, I have written all old. So DEF it is, right? So it will be XAF by XAB minus divided by XAD minus XAB. So this is the ratio of overflow versus underflow. And similarly, if we want to remove D, then we will get B by F, that is underflow versus feed ratio. So that will be XAD minus XAF. Similarly, if you can calculate by yourself also, you can get XAD minus XA divided by XAD minus XAB. Now, what will be the overall effectiveness? So, overall effectiveness will depend on the material. So, overall effectiveness depending on the oversized material. So, it will be amount of oversized material A in the overflow. So, amount of oversized material, because we have in this case we have defined that overflow is our, or desired particle is our in the overflow, right? So we have to define it as amount of desired material A in overflow divided by amount of desired material A in feed. So the calculation will be, so the flow rate into the mass fraction. So in case of overflow, the flow rate is D, and desired material mass fraction is XAD, and it divided by feed, and this is XAF, right? And similarly, or also you can simplify it. So D by F we just written D by F XAF minus XAP in XAB into XAD minus XAB multiplied by XAD into divided by XAF. So this is the expression of effectiveness depending on the material, desired material, and effectiveness depending on the undesired material, it will be similarly amount of undesired material B in the B in the underflow and in the feed. So it will be BXB, no, BXBB. It will be B is our undesired particle. So it will be BXBB and FXBF, right? So BXBB is nothing but the 1 minus XAB. That is, we have to subtract it from the 1. So because the mass fraction is overall mass fraction of the desired and undesired material is 1, so we are subtracting from 1. So it will be similarly F into 1 minus XAF. And again we know the expression of B by F. So that will be XAD minus XAF divided by XAD minus XAB into this 1 minus XAB into 1 minus XAF. And now if we want to know the overall effectiveness factor or overall efficiency, so overall effectiveness is just multiply between the effectiveness of the desired material and effectiveness of the undesired material. So what we have written so far, we have to multiply both of them. And still what we'll get, so we have to multiply this with this. So this is the so this will be the final. So what will be XAF minus XAB, then XAD minus XAF, XAD minus XAF, then XAD into 1 minus XAB divided by bottom portion XAD minus XAB square, because here also XAD minus XAB is there, here also XAD minus XAB is there. So it will be XAD minus XAB whole square into XAF into 1 minus XAF. So this is the final overall effectiveness factor for a screen. So when you're going to solve this, you have to remember the formula.
Okay.
Next, what is screen capacity? What is capacity of a screen?
The feet per unit time to a per unit area screen area.
Yes. So the capacity of a screen is measured by the mass of material that can be fed per unit time. That can be fed per unit time to a unit area of a screen. So this is called the screen capacity. Next, to obtain all maximum effectiveness, the capacity must be small. To obtain maximum effectiveness, the capacity must be small.
True.
Yes, it is true because the capacity and
effectiveness are opposite
effectiveness
factors.
are opposite factors. Yes. So if some screen has high effectiveness, that means it can separate the oversized and undersized material very efficiently. That means the capacity of this screen is low. Next, how is capacity of a screen controlled? How is capacity of a screen controlled?
By the rate of feed to the
Yes,
unit,
by varying the
rate
rate
of feed.
of feed to the unit. Next, the probability of passage of a particle through a screen depends on what? The probability of passage of a particle through a screen depends on what? That means a particle will pass through a screen or not, on which factors it will depend.
Total surface,
Yes.
the diameter of the particle,
Hmm. First one is the fraction of the total surface area. Fraction of total surface area represented by opening. Second one is the ratio of diameter of particle to the width of the opening. To the width of the opening. And third one is the number of contacts between the particle and the screen surface. Between the particle and the screen surface. So in these factors, the probability of the particle depends. Next, how is the largest particle that passes through a screen related to number of openings per screen area?
A 1 upon
Hmm.
dpc square.
Yes. So this one is the so number of openings per screen area is proportional to the 1 by dpc square. And dpc is the largest particle which just passed through a screen. Next, how are the largest particle that passes through a screen related to mass of one particle and the capacity of screen? How are the largest particle?
Is
Tell.
proportional to dpc cube.
Yes, mass of the particle is proportional to dpc cube and capacity is proportional to dpc, just the diameter of the largest particle.
Mass 1 particle 1 upon dpc cube, yeah, only.
Oh, this is dpc cube. Yes. Mass means volume into density. So it will be volume is cube of the diameter, right? So it is dpc cube.
Yes.
Next is, what are the capacity of grizzles and vibrating screen? What are the capacity of grizzles and vibrating screen?
0.05 to 2 is Grizzle
Yes.
and 0.02 to 0.8 vibrating.
So yes, for grizzles, 0.05 to 0.2 ton per feet square hour millimeter, and for excuse me, for vibrating screen it is 0.2 to 0.8 ton per feet square hour millimeter. This is the capacity. Next, the capacity and effectiveness are in general high for particle sizes smaller than about 150 mesh. Is it true or false?
True.
No, it is false, because when the particle size becomes very smaller, it is difficult to separate through screen, and that is why in general it is difficult to calculate the capacity and effectiveness also. So when there is a 150 mesh, that means there are 150 openings inside the screen, and that means the diameter of the openings are very small. So that is why, so that is a very fine mesh. So fine mesh is difficult to calculate capacity and effectiveness. So that is why it is false. It will be a low for particle size. Here it is high, so it will be low for particle sizes smaller than about 150 mesh. So when the particle sizes are very small, the capacity and effectiveness cannot be calculated very easily.
Ma'am, solve the assignment.
Yes, the assignment questions are easy, I thought. Yes, which one?
First is answer root 2.
Yes, yes.
Second is confusion.
In the Tyler standard screen series, if the mesh number increases from 3 to 10, then which one of the following option is correct? Clear opening decreases, right? So when the mesh, so the first slide I have seen, I have shown you that. Oh, just a minute. Here, so when suppose it is a mesh, so the aperture or openings will be reduced, right? When the mesh number will be reduced. So because we want to fit, here suppose it is 20 mesh, and here suppose it is 150 mesh. In the same area we are trying to fix, right? So obviously the mesh opening will be reduced.
Okay. The clear opening decreases.
Yes,
Third one is answer D. Number of opening per unit screen area is proportional to 1 upon dpc square.
DPC square. Huh.
Next is the second. Decrease particle diameter, increase the capacity of the screen.
Decreasing particle diameter increases the capacity of the screen. Yes, yes.
Next, next is numerical solve.
Let me check one second. Oh, it is proportional, no? The capacity of a screen in the effect of mesh size on capacity screen, that is written now, that we have just seen it here. This one. So capacity of a screen is related to the particle size, largest particle diameter. So if it is reduced, then the capacity will also be reduced. So I think increasing particle diameter increases the capacity of screen. This is proportional to the DPC, right? So it
Okay.
should be A.
A answer.
Yes,
Okay.
I might be wrong, but as right now I am thinking
Okay.
this.
Increasing particle diameter and increase the capacity of the screw.
Yes.
Okay. Next is the numerical effectiveness screen.
How much are you getting? It is the effectiveness. This just the formula based problem. How much are you getting?
Okay, ma'am, please solve.
Yes. Okay. A batch of crash dimension was. So it is have just asked the screen effectiveness based on the size. So first is the oversized material is our desired product. Oversized material in feed is 0.73. That is our XAF is 0 0 point how much? 0.73.
7.
Then XAD is
0.97.
0.97 and XAB is
0.58.
0.58. Then it is asked that overall, not overall, it has asked the effectiveness based on the oversized material. So we'll use this formula of EA. So this formula of EA will be used because this is the effectiveness based on the oversized particle, right? So it is XAF minus XAB, XAD minus XAB. So it is XAF minus XAB divided by XAD minus XAB into XAD by XAF, right?
Yes.
Did I write the formula correctly?
Okay.
This is the, now if you put all the values is there. So it will be 0.73 minus 0.58,
Okay.
0.9, 0.58 into 0.97 by 0.73. So how much is it? It is So it is showing 0.51. That means 51%. It is coming as 0.51. So it is 51%. This is the answer.
Okay.
So this is just formula based sum. It is very easy.
Okay. Next is the physical mechanism most effective separate small particles based on their natural random motion. My answer is Brownian diffusion.
Yes, yes. It is Brownian diffusion.
Next, ma'am, it's confusion. The
The
particle setting.
particle settling velocity of a spherical particle in gravitational settling under a laminar flow regime varies linearly with the particle diameter. Yes. So that you have to go to the laminar flow section where sir has taught you. Mhm. Linearly with the particle diameter directly with the viscosity of fluid. Here is the directly with the square of particle diameter because
Directly. Yes.
C, option C.
Okay.
Because if you notice the formula, it is written that in a laminar flow chamber, the collection efficiency, that means the settling efficiency, eta is
Okay.
proportional to
3 beta.
UTL by U bar into H. So UT is the settling velocity of a particle, settling velocity. Then L is the height. L is the not height. L is the length of the plates.
Length of the
Length
yes.
of the plates inside the laminar flow chamber. H is the distance between the plates. Between the plates. And U bar is the mean velocity, mean gas velocity. So now UT, that is the settling velocity. Settling velocity, you have we have solved it, derived it in previous classes. That is, it is rho g, that is rho p, particle density, or into gravitational acceleration into dp square by 18 mu. Yes, so here the relation between, that means ut is proportional to dp square and eta is proportional to dp square and eta is proportional to ut. That means eta is proportional to dp square only. Question is asked of efficiency, right? The velocity of a spherical particle. Not efficiency. It is said just the particle settling velocity. So that means particle settling velocity is directly proportional. So you don't need to look into this also. Only this will be enough. If you remember this formula, so you can remember that ut is proportional to dp square. So ut is the settling velocity, which is directly with the square of the particle diameter. Hmm.
Next is how do electrostatic precipitator remove particle from gas stream? My answer is by using charged particle in an
Yes,
electric field.
yes, yes.
Next is an please solve.
So if you are not solving by yourself, then in the examination you will face difficulty, right? So now I can do, obviously. You practice it because the problems are not that difficult. You have to just go through the formula well.
Okay. Next is in solving problem.
Hmm. So here, what is the question? The question is centrifuge of diameter 0.5 meter in a pilot plant rotates at a speed of 35 hertz. So from for basics, you want to know first what is the centrifuge principle.
Okay.
So if you remember this, you can easily calculate. Centrifuge principle is, so inside a centrifuge, the particles are rotate like this. The particles are rotating like this. And as the particles are rotating, they are feeling a centrifugal force upon them, right? So, and also they are feeling some gravitational force. So these two forces are balancing with each other, and that is why, so centrifugal force and gravitational force are balancing with each other and creating this motion, rotating motion, and centrifuge. Finally, the centrifuge is happening. So for this particle, two centrifugal force is F, that is m omega square r. M is the mass of the particle, r is the radius of the centrifuge, and omega is the rotational speed, right? And gravitational force is G, it is not in general G equals to mg. Now, what is the separational factor? So, separation factor is S equals to F by G. That is, we will just multiply, divide it. So, m omega square divided by mg. So, what will happen? This omega square r by g. So, in the question, omega is given, right? So in the question it is said that diameter of the centrifuge is 0.5 meter and it rotates at a speed of 35 hertz to achieve effective separation. If this centrifuge is scaled up, so in the second case what is happening, the diameter is becoming 2 meter and the same separation factor is to be achieved. So what is the rotational speed? So in the second case, what is the rotational speed? It has asked. So we know from the question that S1 equals to S2, right? Because the rotational separational factor of both the situation is same. It is written here, the same separation factor to be achieved. Okay, so we can write it as S1 equals to S2. So now we can write the similar thing, that is omega 1 square R1 by G equals to omega 2 square R2 by G, and that is nothing but omega 1 square R1 equals to omega 2 square equals to R2, because G is same for everything. So omega 1 square, we know omega 1 square is what? The value 35 hertz, right? Yes.
Okay.
So it is 35 hertz. So it will be 35 whole square into R1. R1 is the diameter is 0.5. So R1 is the radius. So we will take it 0.25. 0.5 by 2. 0.25 equals to omega 2 square is to be calculated, and the new diameter is 2 meter. So that is radius will be 1, right? So omega 2 square will be 0.25 25 into 35 square.
Okay, R2 is 1.
Yes. It is 306.25 and omega 2 will be just 17.5. Is there any answer? 17.5? Yes. Option C.
Next is, ma'am, my answer, centrifugal force increase with increasing viscosity of the medium.
Centrifugal force increases with increasing particle size, increasing viscosity of the medium, increasing density of the medium, increasing speed of the.
Yeah, force.
Option A will be the correct, I think, because in the centrifugal force, what we have said, centrifugal force is m omega square r, right?
Yes.
So it is dependent on the radius.
Okay.
So when the diameter of the particle is increasing, the centrifugal force also increases.
Okay.
So it will be option A.
Okay.
Yes, so it has nothing to do with the viscosity. Yes, obviously it has something to do with viscosity, but density, but directly centrifugal force is dependent on the particle size, because the last option is centrifugal force decreases with increasing speed. That is also not true because it is also proportional to omega square. So the answer will be A. Yes. Okay, anything else?
Okay, ma'am, thank you.
Okay. So I will continue the rest of the lecture. So you can leave if you are done. The next question here it is the capacity and effectiveness. Oh, this is done. Okay. Next question is the industrial sector is responsible for how much percentage of the particulate matter 2.5? Answer is 17%. Answer is 17%. Next question. The term aerosol commonly refers to the particulate and air mixture. Is it true or false?
True.
Yes, it is true. Next question. What are the things need to be checked before designing a particulate emission control system?
Concentration of the particulate.
Yes, it is the concentration of the particulate in the stream.
Gas flow rate.
Hmm. Second one is the gas flow rate. Then size distribution of the particles. And the last one is the allowable particulate rate. Allowable particulate emission rate. What are the operational factors for designing a particulate emission control system?
Pressure, power,
Yes, this is the pressure drop through the unit. Second one is the power required. Third one is the quantity of liquid. Fourth one is the no, that is quantity of liquid or its cover. Next, what are the physical mechanisms for removing particles from gas stream? So there are
sedi-
four. Yes, sedimentation, then
electric charge, then
electric field charge,
inertial
electric
deposition,
field charge, then internal deposition,
and Brownian diffusion.
and Brownian motion or diffusion. So if you see these videos, each one is explained. So this is the sedimentation. So due to gravity and the agitation device, these oversized particles or dust particles are underflow material and they are going down, and clean water is collected from here, which is the overflow water. So this is the sedimentation. Next one is the motion of particles in magnetic and electric fields. So E is the defining as the electric field and B is the magnetic field. So you can see how particles are moving in the effect of electric and magnetic field. So this is the effect of the magnetic field. So this is how it will go. Next one is the Brownian motion. So here the particles are moving randomly in random direction. The smaller the particles, it will be moving much more frequently compared to the bigger particles. So this is the Brownian motion. It will be nicely given here. So here you see that these are the particles, underlying diffusion of particles called Brownian motion, the Brownian movement. Suppose these are water molecules, the larger particles causing them to move in random directions. Different properties of the medium can lead to differences in observed Brownian movement. So suppose in a water, the particles can move in some direction in some way, or inside a glycerol which has higher viscosity than water, the particle movement will be different from there, because in the case of glycerol they have to make extra effort to move, because the viscosity is higher in case of glycerol and viscosity is resisting them there to their free movement. So this is the so when the temperature goes up, the water molecules move faster. So it is also temperature dependent. The Brownian motion or Brownian movement is also temperature dependent. So conversely, if the temperature goes down, the water molecules move slower and the particles move slower. So it is clear. And if the molecules become larger, suppose the medium is very viscous, such as honey or tar, or the way I have said glycerol, the molecules and particles will move slower. Also, it is dependent on the path. So if we narrow down the width of the tube, the particles come close together and the dominant direction of motion is along the length of the tube. This movement is known as the diffusion. So this is the Brownian motion definition. So and that is how, based on this motion, they are separated inside a chamber. This one is the pollen grains of water motion. Pollen grains movement in water. So we can see this, that with the help of Brownian motion, these pollen grains are very smaller in size and they are moving freely in this medium and in random direction. So this is the way it is looking like they are vibrating. They are not vibrating. This is their random Brownian motion. So this is the random Brownian motion of pollen grains in water. Next, what is the key parameter that influences the choice of which device to employ in a particular case? So for separation of particles, what is the key parameter we need to look into? That whether we will use the sedimentation method, whether we will use the Brownian method, whether we will use the charge electric field method. These all the separation methods, these are different separation methods. So for which parameter, depending on which parameter, this differentiation can be done.
dp.
Yes, this is the diameter of the particle. So suppose this bigger particles. So for bigger particles, we don't do the Brownian. For bigger particles, we'll do sedimentation.
Okay.
For finer particles, we'll do Brownian. For charged particles, we'll do electrostatic separation. So that is how.
Okay.
Next, what are the equipment used for removing particles for gas stream? So there are different. So settling chamber, gravity chamber, cyclone, electrostatic precipitator, filters, and wet scrubbers. So if you see this is the So right here you can see that something is coming, the mixture is coming, and it is filling up the partitions, and if there are some dart inside it, so they will separate depending on the size in each of the partition. So if you see this video, it will be clear. The simulation though. So this is the inlet, this is the chamber length. So you can see that depending on this size and depending on the gravity, these particles are separated between the two containers. So there is a baffle due to which some of the particles are already stored here, and some of which are passing through this, and they are separated in the next section. That is how you can separate bigger particles from a mixture. Next one is the cyclone separator. This is the inlet flow with the particles from the process. From top, this is the outlet flow. Then this is the cyclone. This is the deflate valve and the particle container. So we can optimize the cyclone depending on the height, and depending on the particle, depending on our requirement, we can change the size of the particles, change the shape of the cyclone separator. So you can see how. So particles are coming and they are rotating in this rotor, and fine particles are going from top and the heavy particles are separated from the bottom. So this is how. So you can see that bigger particles are settled down. This is the cyclone separator. Next one is the electrostatic precipitator. Chamber, inside the chamber they are connected to the ground. One side is connected to ground and another side is connected to the electric field. Plates are discharged electrodes. The electrodes are negatively charged with high voltages and are insulated from ground. As the fluid gas flows through the chamber, the dust particles and other entrant flue gas components pass through the high energy field. So fluid gas is passing through this chamber, and these chambers are insulated and they are negatively charged. And this gas will be ionized easily because there is electric field. And these positively charged particles are caught builds up in the positively charged chambers are catching all the dust particles, and the clear gas is passing through the chamber. So here you can see more clearly. So how a gas laden with dust particles is coming, and they are separated in this middle portion, and these particles are getting settled down because of the electrostatic force, and the clean gas is separated.
Okay. Lock कर दिए.
So here they are showing at four discharge plates or discharge electrodes. This is a gas distribution plate, discharge electrodes, collection surfaces, and wrappers. So you can see the gas is coming. These particles are getting attached to the chambers, and they are finally settling down, and clean gas is going out. And this is this is happening in four chambers, which will give us more clear gas. So as many as 14 fields or series of discharge electrodes can also be there. So you can see here how these charges are. So you can see that when the particles are touching this positively charged ions, they are inducing positive charge, and they are easily attracted to the negatively charged electrodes. And they are attached to that because of their potential difference. So this is how the electrostatic separator works, or precipitator works. Next one is the bag filter. So here the fluids are going, and they are discharged. This is a very basic filter. This one is the wet scrubber. So wet scrubber mainly deals with the acid and alkali waste gases. Okay, so when the gas enters the scrubber tangentially from the air inlet at the down of the scrubber body, the power of the fan, it quickly fills the space of the inlet reaction. On the surface of the packing, acid gases or the alkaline gas undergoes an acid-base neutralization reaction with the chemicals in the liquid. An unreacted gas continues to rise into the upper layer. So here you are seeing in every stage there is some fluid distribution to make the system wet. It will be more clear from this one. So this is the wet scrubber for cleaning process. So everything is coming from this pipe, electronics, food, pharmaceuticals, and they are before mixing directly to the environment, they are first going through the chamber of wet scrubber where they are mixed first to the water. So their harmful components will be released. Neutralize the harmful components in industrial gas streams. So this is the first step. Along the water molecules, these feed molecules are also going up. Okay. So gaseous compound dissolve and remain in the neutralizer liquor. This is the second step. And now dissolve. They are going upper in the second step, and at each stage there is a flow of water. Process requirements are determined according to certain chemical as well as heat and balance calculations. Obviously. So finally, this water makes them less harmful to the environment, and finally, these particles eliminate the harmful gases up to 99%. So these particles are already settled, and only the pure gas is going to the nature. Okay, so this is the wet collection device. Okay, next question. What is collection efficiency of an equipment? What is collection efficiency of an equipment? What is collection efficiency of an equipment?
Okay, ma'am. Thank you. The college timing is 4:30. So
Yes, yes. Okay, fine.
thank you very much, ma'am. है ना,
Welcome.
for and guidance for the doubts and solid follow doctor.
Okay, okay.
Thank you, ma'am.
Welcome. So the collection efficiency is a function of diameter of the particle, it is 1 minus number of particles of diameter dp per meter cube of gas out divided by number of particles of diameter dp per meter cube of gas in. Okay, so how much how much particles are there in per volume of the gas that is going out, and number of particles mm, of diameter, certain diameter is in per volume of gas that is going in, has to be subtracted from 1. This is our collection efficiency. Next, what is penetration based on particle mass of an equipment? What is penetration based on particle mass of an equipment? So it is, penetration is Pm, that is 1 minus eta m, that is 1 minus the efficiency. Okay, so penetration is 1 minus the efficiency. Next, settling chamber has large pressure drop. Is it true or false? Settling chamber has large pressure drop. The answer is false, because it has low pressure drop. Low pressure drop. Next, what are the basic idealized flow situations? What are the basic idealized flow situations? First one is the laminar flow, where the particles move or fluid move in layer by layer. Okay. Second one is the plug flow with no vertical mixing. Plug flow with no vertical mixing. That is step input. It is like step input. Suppose there is a pipe, so at different flow rate, this portion of the particles are portion of the fluid is moving, and there is no separate mixing along the vertical direction. And the third one is the plug flow with mixing, vertical mixing. With vertical mixing. Okay, so it will be clear from the video itself. So notice carefully that we are putting different types of different viscosity fluid initially. This is another fluid of different viscosity. And this is the third fluid. Now we are rotating it from the top very slowly. So what will happen? They will go layer by layer. They are not mixing with each other. You can see that they are not mixing with each other. They are going layer by layer. Right? Now if we are rotating in opposite direction, what will happen? You can see that they are coming back. They have come back to their original position, right? So this is the laminar flow. They are not mixing with each other. Next is the plug flow without vertical mixing. So you can see this is a step input. After one step, they are stepwise they are inputting. They right? So you can see this is the step input. Next one is the plug flow with vertical mixing. You can see there is a mix in the vertical direction but not radial direction, right? So this is the plug flow with vertical mixing. Next, what is collection efficiency curve? What is collection efficiency curve? So in the collection efficiency curve, it shows the position of the low mixing laminar mixing plug flow. Plug flow without vertical mixing and with vertical mixing. Though it is ratio of UTL by U bar H, that is root of the efficiency with this. Okay. So suppose this is 0, 0.2, 0.4, 0.6, 0.8 like this. It is going. And here also it is 0.2, 0.4, 0.6 like it is in the top also it is going. So when this is its curve, it is efficiency is high but with respect to some degree of mixing. So it is the plug flow, no mixing. Second one, when the curve is little bit of S shape, that is plug flow with vertical mixing. Plug flow with vertical mixing. And finally, it is complete mixing, that is turbulent flow also you can tell. Complete mixing, plug flow. Okay, so this is the collection efficiency curve. Sure. Excuse me. Next, what is the force acted upon a particle inside a centrifugal separator? Inside a centrifugal separator, the centrifugal force is m v theta square by r. M is the mass of the particle, r is the radius of the cyclone separator, and v theta is the angular velocity. Okay, right? Next, the length of the body of a cyclone is related through the gas flow rate to the number of turns executed by the gas stream. The length of the body of a cyclone is related through the gas flow rate of the number of turns executed by the gas stream. It is saying the length of the body is related to the gas flow rate due to which it will take turn. Right? So the answer is true. It is related. All things are related. Next. The radial velocity component is the terminal velocity of the particle when acted on by the centrifugal force. The radial velocity component is the terminal velocity of the particle when acted on the centrifugal force. The answer is true. Radial velocity acts as a terminal velocity inside a centrifuge or cyclone separator. Next, calculate the radial component of a velocity for a cyclone. So, inside a cyclone, you will notice the radial velocity is dependent on the centrifugal force of the particle and due to drag how much it is moving, right? So that centrifugal force is dependent on the 3 pi mu dp because that is in laminar zone. You remember the formula F equals to 3 pi mu dp u. We used to write it as u, but here it is the radial velocity component. And v theta, that is the rotational velocity component, is q divided by wr ln r2 by r1, where w is the width, okay, width of the chamber, then dp is the particle that is moving, u is the velocity, q is the volumetric flow rate of the particle, volumetric flow rate of the fluids, and rho p is the density of the particle. Okay. Now, what is Fc? Centrifugal force can also be defined as mp v theta square by r, right? That is mp is the mass of the particle, this is the rotational velocity squared by r. And mass of the particle means nothing but the density and the density multiplied by the volume of the particle, that is pi by 6 rho p dp cube, and v theta square by r keeps as it is, and then it will be pi by 6 rho p dp cube. Now we know the v theta expression, that is q square divided by r is already there, that means r cube, w square ln r2 by r1 square. Okay. Now put all these value in the VR. So what it will come? If we put everything in VR, if we put everything in VR, what is VR is additional velocity Fc by 3 pi mu dp. So Fc we now know, that is rho p, right, q square dp. Okay, let me write it clearly. So VR is Fc. So Fc just we have seen pi by 6 rho p dp cube q square by r cube omega square ln r2 by r1 এর whole square, right? This is the Fc divided by 1 by 3 pi mu dp. So final expression is, so this pi and pi will be cancelled out. 1 dp will be cancelled out. It will be rho p q square dp square divided by 6 into 3 18 mu r cube w square ln r2 by r1 এর whole square. So this is the expression of your velocity, radial component of a velocity for a cyclone. Next, name the variables affect on cyclone collection efficiency. Name the variables affect on cyclone collection efficiency. Okay. Name the controlling parameter to which has effect on cyclone collection efficiency. So first one is the particle size. Second one is the particle density. Third one is the inlet gas velocity. Cyclone body length. Number of gas revolutions. The last one is the smoothness of the cyclone wall. Okay. Another list is there, which is cyclone diameter, then gas outlet duct diameter, then gas inlet area. Okay, so what will happen if these things increase? Collection efficiency increase. So it means they increase collection efficiency increases. But in this case, they decrease collection efficiency increases. So if cyclone diameter decreases, then collection efficiency is increased. But if the particle size is increased, cyclone collection efficiency will be increased. Okay, so these are the two difference between these two variables. Next, the centrifugal acceleration makes the suspended particles move in a tangential direction towards the outward direction. Is it true or false? The answer is true, because inside a cyclone separator, the particles are moving in this way. So they are moving in a tangential direction which is outward, so that they get separated, right? So that is why this is true. Okay. So, okay. I hope this the question I have solved today, it will be helpful for you to solve the assignment equation, assignment problems, and also you need to yourself solve this question, because in the examination this type of question only will come. Okay, so keep in that mind, and we'll meet on next Saturday. Till then, goodbye.